So I'm Rachel Smith. I'm the head of the Astronomy and Astrophysics Research Lab at the museum. And I'm also a professor at App State. And I'm excited to introduce our next speaker. And that's why I'm here. I'm just, there are a few speakers I'll be introducing for Astronomy Days. And this next speaker is Dr. Jessica Barnes. She will be discussing the value of moon samples. And Dr. Barnes is an assistant professor at the Lunar and Planetary Laboratory at the University of Arizona. She received her PhD in 2015 from the Open University and the Natural History Museum in London. And just as I know Jessica will be telling us about her research using Apollo samples, which is really interesting. Remember, Apollo was way back in the 1960s and 70s. And so these are old samples, and she will tell us why they're being used now. And basically, Dr. Barnes's lab utilizes a combination of techniques to study the mineralogy, geochemistry, and other types of history of a wide range of extraterrestrial materials. So anything extraterrestrials off this Earth, and these materials today that she'll be talking about to us are from the moon, and you may think of other types of extraterrestrial materials, but today's topic is about the lunar samples. So without further ado, I will pass it off to Dr. Barnes. Thank you.
Thank you very much for the introduction, Rachel. I will share my screen and hopefully everything will go okay. Let me go full screen mode. Okay, so hopefully you're seeing my screen. Rachel, can you?
Yes, we can see it.
Brilliant, thank you. Okay, so let's kick it off. So as Rachel and Sam both said, today, I'm going to talk about the scientific value of lunar samples. And I just kind of wanted to preface this talk by saying that, you know, planetary science is really focused on understanding how planetary bodies formed and how they evolved to their current state over time. And planetary science is all about deciphering the processes that occur today and in the past. And so we can learn an awful lot about a planetary body by going to that planetary body and observing it remotely from orbit, or going to its surface and using rovers or humans. And we can also study planetary bodies from here on Earth using telescopic observations. But for a planetary geologist like myself, there's nothing better than going and getting samples or having samples in your hands to study. But it's really important too that we understand the ground truth of that sample. So that's the beauty of going with robots to collect samples, or humans, is that they can contextualize where that sample came from. And not only do we have the sample in our hands on Earth to look in more detail in terrestrial laboratories, but we understand where it came from. What were the rocks around that sample? What did they look like? What was the surface from which that sample was collected? And so there are two main ways that we can study samples from extraterrestrial bodies, like Rachel mentioned, here on Earth. We can either look at samples that have been returned or brought to Earth from other bodies by humans or human-assisted ways like robots or spacecraft, or we can use meteorites that are pieces of extraterrestrial worlds that make their way to Earth, and then we find them, and because they're very different to the rocks we find on Earth, we can categorize them as extraterrestrial materials. But today I'm going to focus on the moon, and I'm going to focus on samples that have been brought to Earth by human-assisted means, whether that be spacecraft, robots, or humans. Okay, and so in total, there have been 10 landed missions that went to the moon, collected samples, and brought them back. The first 9 all occurred, like Rachel said, in the 1960s and 70s. And so the first lunar mission to go and collect samples, land successfully, and take humans with it was Apollo 11, of course, in 1969, when Buzz Aldrin and Neil Armstrong landed on the surface of the moon in Mare Tranquillitatis. Apollo 11 was followed by another 5 successful landed missions that landed, explored, and collect samples and brought them back. And those were Apollo 12, 14, 15, 16, and 17. And in total, the Apollo missions collected over 380 kilograms worth of rocks and soils and brought them back to Earth. In addition to those kind of 6 famous NASA missions, there are also 3 famous Soviet Union missions that brought back material robotically, not with humans, from just outside the region where the Apollo missions went. And so these were Luna 16, 20, and 24. Now, the big difference between the amount of material brought back, so I just mentioned Apollo collected just over 382 kilograms, the robotic Luna missions only collected around 300 grams of material. And that's purely because the Luna missions were robotic. They weren't designed to collect large amounts of material. They weren't necessarily exploring large regions of the surface, whereas the Apollo missions had more capacity to carry material, and also they had humans to look around the surface and actually bring that material back. And I'll talk a little bit at the end of the presentation that after a 50-year hiatus in going to the moon and collecting samples, there was a recent Chinese mission, the Chang'e 5 mission, that actually went to the lunar surface outside of this region explored 50 years ago. And recently, just before Christmas, collected and brought back another, we think, approximately kilograms worth of material. Okay, but for today, what I want to do is focus on a couple of ways in which we have learned about the moon from using Apollo samples. And I want to start with the very first Apollo mission, Apollo 11. So for anyone who's not familiar with Apollo 11, it was the first landed mission to the moon with humans. And it explored this region of Mare Tranquillitatis, or the Sea of Tranquility. And what you see here is a really high resolution photograph taken by NASA's Lunar Reconnaissance orbiter that is orbiting the moon today. And from this, you can actually see not only the lunar module that's still present on the surface today, but you can also see the tracks taken by the astronauts. And I've just blown this up here because this is another Lunar Reconnaissance Orbiter camera image, but superimposed on top of that, you see the tracks of the astronauts. So in green, we have the footprints or the tracks of Buzz Aldrin as he was walking around the surface. And in orange, we see those of Neil Armstrong. Now, what's immediately apparent is if you look at the scale bars, the astronauts didn't explore very far. In fact, they only had about 2.5 hours to explore the lunar surface before they had to head back to the lunar module and lift off again and come back to Earth. But in those 2.5 hours, they were able to collect, they were able to move around, deploy experiments, take photographs, take observations, and also collect samples from the region that they visited, even if it wasn't a very large region. Now, I want to put this into probably a perspective that you're more familiar with, which is if we take those same tracks and we put them on top of the Sea, Air and Space Museum, the Intrepid vessel in New York, you can even see humans down here. These little dots are all humans. They didn't really explore a very large region. And so imagine you go to an extraterrestrial world and you only have a couple of hours and you can only travel a few hundred meters. You're not going to learn an awful lot about that planetary body. But when you collect samples, you then have a tool with which to understand that planet, even if you don't travel very far while you're exploring. And so even though they didn't go very far, the rocks that they brought back on that mission have really helped to establish and transform the way we think our Earth-Moon system formed and evolved. And I want to explain one of those kind of findings to you today. So we all know that when we look up at the moon on a really clear night sky and we see the whole moon, we see two very distinct regions on the surface. We see really light areas and really dark areas. Now, even just looking at through a really high resolution telescope, or even looking at some of the orbital images, we know that this lighter region is higher in elevation. It's more rugged. It has lots of pocket marked holes on it created by impacts, but it's this lighter color, and we refer to this as the Highlands region. What we also see are the darker plains. We see these darker, low-lying areas that are generally smooth, and they fill these large circular structures, which are really massive impact basins created by impacts that occurred in the past with the surface of the moon, either from asteroids or comets. Now, it was through the very first studies of the Apollo 11 samples that we began to take this kind of image that we know and these observations we can make at night looking up at the moon, and actually put some chemistry and some time stamp into how the moon got the way it is. How did these light areas and these dark areas actually form? This is a picture of an Apollo 11 soil sample. So a lot of the materials that were brought back from Apollo 11 were soils. And soils on the moon, they're not like soils we find on Earth. They're made up of little tiny rock fragments. And the amazing thing that they noticed when these first samples were studied is that the variety of rocklets that are found within these soils. We find volcanic samples, we find glasses, we find all these different materials that are formed by different mechanisms and have all been jumbled together via impacts occurring through time on the moon. Now, arguably one of the most important findings from studying soils like this was the discovery of this rock type called an orthosite. It's a really milky looking rock that's composed almost entirely of one mineral, and that's plagioclase feldspar. Now, feldspar is not an exotic mineral. It's one of the most common rock-forming minerals on Earth. But to find the rock type made almost solely of that mineral is quite rare on Earth. We don't find an orthosite in huge abundances on the Earth's surface. But what you can see from this image is that this anorthosite is a very similar color to the lunar highlands. And so some of the very first models for how our moon formed and evolved after studying these samples are still around today because they make the most sense for how we understand how the moon formed and evolved. So the question that they started with was, how can we form really large regions, potentially the whole moon made of this anorthosite, when we don't see it on the surface of the Earth, for example? We only see it in tiny abundances. And for that, in order to understand how we get there, we have to go back in time and think about what the moon looked like when it first formed, when it first accreted, and when the material came together after the giant impact event. Now, we think that the moon kind of started off like this. I love this illustration because it really captures the moon as it was hot, but also as it was cooling. Because remember, any heat that's lost from a hot body like this in space is going to radiate out to space, be lost, and essentially cool the body down. And so what happens when you start cooling the molten moon? You start forming crystals. And so that's the basis for this model called the Lunar Magma Ocean model. Essentially, the moon started off as a big magma body, big molten body, completely molten or partially molten. It's really nicely illustrated in this schematic. So here's our beginning point. The moon started molten, this magma ocean, and the arrows indicate that we're losing heat to space. As you start cooling a body like that, you're going to start forming crystals, which is indicated in the second diagram or a second panel. And the minerals that you form are predictable. The first minerals that are going to fall out of this type of magma body are going to be rich in elements like magnesium and iron. And these elements form the minerals olivine and pyroxene, which again are common rock-forming minerals on Earth. As those minerals crystallize, as you can see here, from that magma body, they're more dense than the liquid in which they've just crystallized from. And so because they're more dense, they're going to sink to the bottom of that magma body. And this process repeats itself over and over again until you build up a layer or layers of all these crystals that have formed. The problem with building up these layers is that you're changing the composition, the chemistry of the melt that remains. And so at some point in time, after about 70 to 80% crystallization of this, what we call cumulate pile in the mantle, your liquid that's remaining is going to have changed composition to the point where you can start crystallizing this plagioclase. Remember, the mineral that forms up the anorthosite. But plagioclase is different. It's lighter than the liquid in which it's been forming. And so instead of sinking, it's going to float. And so this led to the idea that we can create these really vast regions of anorthosite and build up the crust of the moon from this mineral. because it floats and forms a flotation crust. And then as you progressively crystallize more and more of this plagioclase, the crust is going to thicken. And so at the end, you're left with just a small residual melt layer that will eventually crystallize as well. And so we think, in a nutshell, that's how the moon went from being a molten state to being crystallized, to being not quite the body we see today, but at least have rocks that we can recognize on its surface, the highlands crust. And this took, it's debated exactly how long it took, anywhere from a few million years up to several hundreds of millions of years to crystallize the crust of the moon and the moon itself. To the body that we see today, and we have the crust made up of that and orthosite in large amounts.
And we had a quick clarification question.
Mm-hmm.
So there was wondering, I'm probably going to mispronounce this, but the material that you were talking about,
anorthosite.
Anorthosite, yes. Mm-hmm. That's you said that was made of feldspar, correct?
Exactly. Yeah.
Okay, great.
And so feldspar, I'll just backtrack a little bit. Feldspar is an calcium aluminium silicate. So it's a type of mineral that takes in calcium, silicon, and aluminium. But crucially, it's less dense than those other minerals I mentioned, the olivines and the pyroxenes, which take in heavier elements.
And that's why it floats to like the
exactly.
crust
That's why it floats on the liquid, because the liquid is at that point is really rich in iron, so it's more dense than those feldspar minerals. And so it's really elegant model that seems to work to explain how we get this much feldspar on the surface of the moon.
Yeah. All right. Thank you.
No problem. And I will just follow up with that question with, we see this, it's possible that a similar process happened on the Earth, for example, but the Earth has something the moon doesn't have, which is plate tectonics. And so on Earth, crustal material is constantly being recycled and regenerated. And so we've lost a lot of the earliest history on the Earth, but the moon is a time capsule. It doesn't have plate tectonics. And so it can preserve, its very earliest history all the way through to the present day. Anyway, so that was Apollo 11. We've made some really, as I say, elegant models to understand how the moon thermally evolved. And those models are still, in most part, used today and widely accepted, which is amazing that after 50 years of studying these samples, we still kind of take those models. There are some tweaks, but generally they still hold true. I wanted to talk now about the Apollo 17 mission and some of the samples brought back from there. And if you've been to the Museum of Natural Sciences, then you've probably seen an Apollo 17 rock. In fact, I think it's a touchable rock as well. And that's Apollo 17 sample 70017. The main difference between the Apollo 11 and 17 missions, if we just look at those two, was that on Apollo 17, they had a vehicle, right? They had basically a lunar car that they were able to take around the lunar surface, travel further distances, and collect samples and explore a wider area. And so this is illustrated really nicely on this Google image where you can see the Intrepid Sea, Air and Space Museum here. Obviously, the tracks that we were looking at, you can't even see them from this image. But this is essentially Apollo 11. These orange tracks are the tracks that Eugene Cernan and Harrison Smith took on Apollo 17. So here's the lunar module in red, and then the orange tracks represent the 3 different extravehicular activities or expeditions, if you like, the EVAs, that they took over their 12-day stay on the lunar surface. Now, or they weren't on the surface for 12 days. The entire mission was 12 days, but the 3 EVAs that they took while they were on the surface. So in comparison to Apollo 11, they had a longer time on the lunar surface. I think they were there on the surface for 75 hours, something like that. So a longer time. And also they had this freedom to move around on the surface using the rover. Because remember, it would have been really arduous to move around and operate on the lunar surface in those big spacesuits. So having the rover help them not only travel longer distances, but I guess also have some break because they were able to drive around. So that gives you a feel for the difference in terms of the time that they were on the surface and how the distance they were able to explore. This is a similar image, but showing you now the tracks on top of a Lunar Reconnaissance Orbiter camera image, which shows you exactly where they went, and even shows you some of the craters that they were visiting along the way, or stop-offs that they had. All of these little points represent areas where they stopped at. And a neat thing that I wanted to show is that now we have such good resolution from orbit today with LRO that we're able to see in amazing detail what the astronauts were actually doing on the surface. So not only can we see the tracks and link them like has been done here to where they were exploring, but we can also see in more detail what they were sampling at the surface. And so what I mean by that is, look at this image here from LROC, from Lunar Reconnaissance Orbiter camera. We can see the tracks of where the astronauts were going, but we can also see things that they sampled. So here is a boulder trail. So it's a track made by a boulder that's fallen down a slope on the surface. We see that there's one boulder at the end of it, but we also see there's a cluster of boulders around it, and there's a little crater. Now we can directly relate that to sketches taken by the astronauts in their photography at the time, and link those directly to samples that were collected from these different objects, which I think is just amazing that we're able to piece all of this together now with this high resolution imagery. And so you can see that indicated in this sketch. So here we have the boulder tracks highlighted in red. This pink rock is that big boulder at the bottom of the boulder trail. And then you can see there are several other boulders which were also sampled. And we know they were sampled because you can see these blue lines and the sample numbers. So all of these numbers beginning with a 7 indicate that these are rocks or soils collected from Apollo 17. So now we can place even orbital imagery. We can tie that to analyses made on samples and come up with a history, because clearly this rock did not originate where it was sampled on the surface. It originated back up that boulder trail at a higher elevation. Now, one of the other fascinating things about Apollo 17 is that was the discovery of this orange soil, these orange volcanic deposits on the surface of the moon. And so you can see a really nice image here from Apollo 17 where you can see clearly this orange soil that looks very different to the kind of grays, and I don't want to say it, but kind of the bland scenery of the moon that we see surrounding it. And so you can see the orangeness that this soil has when we look at it under a microscope, or even on a petri dish or something. We can see that the soil is made up of these little orange spherules that you see in the middle image. And these are volcanic glasses. We think that these materials formed in the past by volcanic eruptions that essentially erupted lava into the vacuum of space. And because the moon doesn't have an atmosphere, those beads would have been hot enough and would have quenched, essentially froze, if you like, in space, and then would have rained down onto the surrounding area. And you can see that in the little schematic, that we have these little molten droplets freezing in space and then raining down onto the surrounding area. And so we think that's how these deposits were formed, and we think they're over 3 billion years old, these particular orange glasses. Now, the glasses themselves are really interesting because they help us to understand volcanic processes on the moon, and allow us to compare what happened on the moon in the past to what's happening on Earth today. But more than that, they've been really crucial in helping us to make several other discoveries. And so a lot of my research has been involved in understanding if the moon has any water. And the Apollo era legacy really found that the moon is bone dry. So work that was done on lunar samples in the 70s and 80s didn't really have the resolution or the capacity to measure very small quantities of water in lunar samples. They did measure water in the lunar samples, but they couldn't disentangle whether they were measuring something that was truly moon water or whether it was terrestrial contamination. And so the basic conclusion was that the moon didn't have any water. And then that conclusion was fed into the way in which people modeled how the moon formed, how the giant impact worked, how the moon evolved after that giant impact. And so the moon was bone dry. But in the late 1990s, early 2000s, mid 2000s, several different spacecraft started detecting hydroxyl and water ice on the lunar surface. And not only at the polar regions, like you can see here in this image, which is a global mosaic of spectroscopy data from the moon, where blues and purples represent detections of water ice. But actually, since then, we found water ice and water in various forms on the surface of the moon, all across its surface. These findings really prompted us in the late 2000s to go back and look at lunar samples, because in the intervening 30, 40 years, significant advancements have been made in analytical techniques, so laboratory equipment, that actually allow us to measure very tiny amounts of water. And so maybe applying those new techniques to old samples could reveal something new. And lo and behold, in 2008, a study was published that unequivocally found water in lunar samples for the very first time. And this was a huge deal and was followed up by several other studies that found water not only in those glass beads that I showed you a moment ago, those volcanic rocks, but also in melt inclusions. And if you're not familiar with what melt inclusions are, they're fascinating phenomena where you get little parcels of magma being trapped within crystals. And if they're preserved in the correct way, they can tell you about what the magma was, the chemistry, and other conditions of that magma, what that was like while that magma was either erupting to the surface in a volcanic setting, or whether it was being intruded into the crust in an intrusive setting. And so various studies since 2008 have found water in a variety of different types of lunar samples, and have really helped us and change the way we think about the moon. The moon is no longer, bone dry. It's no longer devoid of water. There's not huge amounts of water there inside the rocks. But it's there, and we need to take it into account when thinking about how the moon formed and evolved, not just from the giant impact, but how that lunar magma ocean I talked about at the beginning, how much water was in there? What happened to the rocks that formed from that magma ocean? Did they contain water? And try and piece it together based on the observations that are being made. Now, what I've been talking about so far has been the study of Apollo samples that have been around for the last 50 years, available for study. Now, a few years ago, NASA decided that it was time to reveal some samples that had not been studied before. So NASA had the foresight in the 60s and 70s to set aside a group of samples that were collected during the Apollo era and preserve them unstudied for future generations. They realized that there would be a time when technology would have increased so much that we'd be able to make new discoveries on Apollo samples. And so they wanted to make sure that there were some samples left aside for that day. And so NASA decided a couple of years ago that this was the time, that we had reached that time, that pivotal point where we could start studying some of these unstudied lunar samples. And the program under which we're doing that is the Apollo Next Generation Sample Analysis Program. And so we are currently studying some unstudied and what were unopened samples that have now been made available. And so you may have seen some press releases about this last year or the year before. The first sample in this program that was opened was a core sample taken from Apollo 17. And so on the top image, let me just go back one, the top image is it's an X-ray image, kind of like when you get an MRI scan or an X-ray image at the doctor's office. Similar kind of thing, except here we're scanning rocks, not humans. This is an X-ray scan of that core sample before it was put into long-term storage. You can see some details, so you can see that there are some clasts, but we can't see the nitty-gritty details of this sample. It was put in storage, kept there for the last 40 years, and then when NASA announced that we were going to start studying it, we had it scanned again using new state-of-the-art X-ray scanners. And here you can see the difference. You can see a huge amount of detail, and this is a compressed image. I'll provide links to the museum staff for the high-resolution videos, but this is a compressed image, but you can still see so much detail. There are thousands of individual sliced images that go into this composite, and so we can just tell a huge amount of detail down to the micrometer scale without even touching the sample. So this sample was still in its container, it hadn't been opened, and yet we can start to understand so much from it just by looking at these types of images. In late 2019, the sample was opened at NASA's Johnson Space Center. So here you can see the curation staff who are looking at the sample that has now been revealed for the first time in the glove box. And you can see a higher resolution image here of what that soil looks like, that core. Unsurprisingly, it looks gray, which shouldn't surprise anybody because all the images most of them that we have from the lunar surface, lunar rocks are gray or variations on gray, except for those orange soils and some other unique examples. And since then, this core has been, the curation staff have been dissecting it and sending out pieces to the science team to start unraveling what does this sample tell us about the moon that we didn't know before, and what information can we get that may change the way we think about how these types of rocks formed and evolved. And so that work is still ongoing, but what I wanted to show on this slide is that lunar science really is anchored by samples. Samples shape the way we think the moon has formed, and then in coordination with remote observations, we can start to test some of the theories we make on the samples and vice versa. Things that we see remotely, we then go and look for in the samples to see if we can see a record of it in our laboratories. Studies of lunar samples have helped us to understand how thick the lunar crust is, understand its gravity, its porosity, understand its impact history. So how old are the impacts that we see preserved on the surface of the moon, those pocket marks? Obviously, studying samples in the laboratory allows us to get a handle on the geochemistry, the mineralogy, like I explained earlier. We can also look at magnetism. So some rocks record a magnetic field, and we can look at how that changed through time by studying samples. We also get meteorites coming from the moon. So it's not just bodies like asteroids or Mars that we get meteorites from. We have lunar meteorites. And so lunar meteorites are great because they provide almost a random sampling of the lunar surface. We can essentially study for free wider areas of the moon than we can or have been studied by Apollo and Luna and now Chang'e 5, because meteorites come from essentially anywhere on the moon. But that also has a caveat in that we don't know exactly where they're from. So whereas the Apollo or sample return missions allow us context, we know where those samples came from. The meteorites provide a more global sampling, but we don't exactly know where they came from. And then we also have exogenous material. So we have material inside some lunar rocks that isn't lunar. We have preserved materials from asteroids, for example, preserved inside lunar rocks. And so that helps us to understand what types of material was impacting the surface of the moon over time, and helps us to not only understand how the moon evolved, but how the solar system evolved to what we see today. Now, you may be sitting there thinking, well, problem solved. Like we've got all the samples that we need. We don't need to go back to the moon. We know lots already. But as I've hopefully conveyed to you, we haven't sampled a wide range. We haven't sampled a huge area on the moon. And as this laundry list of kind of my wish list materials to bring back, we still have a lot of unanswered questions. So for example, we don't have any materials in our sample collection of the mantle of the moon. On Earth, we have peridotites and materials that are brought up by deeply plumbed volcanic systems. So we understand a lot about the mantle of the Earth, what's underneath our feet. But we don't have that for the moon, and that would really be helpful to understand not only what is the interior composition of the moon, but help us to test the models we have for how the thermal evolution of the moon happened. We also have this massive basin on the south polar region of the moon. That's one of the largest basins in our solar system. It's an impact structure that we think formed more than 4 billion years ago. And we don't have any sample. We don't think we have any samples from this basin. But if we got samples, that would really help us to understand and pin down the cratering chronology, not just for the moon, but for the entire solar system. We also don't have any samples of water ice. We've detected water inside lunar samples, but that's different to the material that we see on the surface, that water ice or that hydroxyl that we see in the polar regions, for example. And I could go through the whole list, but there are a lot of different materials that we still need to get to fully understand how the moon formed. And then we can use those types of materials to better understand other planetary bodies that are harder to get to. Now, one of the objects or one of the materials on this list are young Mare basalts. And what I mean by that are we in the Apollo collection and in the lunar collection in general, we have ancient materials, but we see evidence on the surface from remote sensing that there's evidence for very young volcanic deposits on the lunar near side. And so that's what the Chang'e 5 mission that just went to the moon last December was aiming to get and bring back to Earth. So Chang'e 5 landed, as I say, in December on the lunar near side. Here is a map of estimates of different volcanic deposits and their ages. So you can see that we have volcanic lava flows or strata or deposits that are anywhere from about 3.5 billion years old all the way down to around 1.3 billion years old. For context, the lunar sample collection we have on Earth dates to around 2.9 billion years old. And so we don't have anything that's on the order of a billion years. So there's a whole billion years of volcanic history from the moon that we don't have access to. And so that was one of the motivating reason for the Chinese mission to go there. And so they specifically landed in that area. This is a really beautiful panorama image from when that vehicle landed on the surface. And you can see the really beautiful flat terrain because they landed in one of these large volcanic areas. It's nice and smooth, very good for doing exploration when you want to land somewhere that's safe. And so they collected some of this material, and we're hoping that in the next few years that we'll understand exactly what the chronology that those samples have to offer. And because the Chang'e 5 mission landed outside of the region that Apollo and Luna sampled, will hopefully help us to better understand the diversity of lunar rock types and what that means for the magmatic and thermal evolution of the moon. But we don't just stop there. So we've done, we think, the young volcanic samples, but there's still a lot to learn. And so looking to the future and what kind of samples we might get back in the future, I'm most excited about the potential for exploring the lunar poles. And so you can see here a relatively new data set from the lunar South Pole, where all of the green dots are indicating high abundances of ices, indicated in some of these really deep and shadowed craters at the lunar South Pole. And so these ice exposures have been detected by a variety of different instruments. So these are the acronyms for different instruments that have been in orbit around the moon. And so these are the type locations or the most interesting locations people are thinking to go to collect, to study in situ, and then at some point in the future, collect some of these ices. Just to give you a flavor for the the range of missions. It's not just NASA that's involved in and interested in going back to the moon to study these volatiles, these hydrogen, carbon, oxygen-bearing species. But ESA, the European Space Agency, is also interested. So they have a mission called Prospect, which stands for Package for Resource Observation and In Situ Prospecting for Exploration, Commercial Exploitation, and Transportation. And so they anticipate that this instrument package is going to be included on the Russian-led Luna 27 mission that is slated for around 2022 or 2023 to be deployed on the lunar surface in the South Polar region. In addition, as part of NASA's plan to go back to the moon, NASA has selected the Viper mission, which is the Volatiles Investigating Polar Exploration rover, to also go to the lunar South Pole to get a close-up view of the location and potential area in which these ices are concentrated and understand exactly how much is there and how it varies. This will have the capacity to rove around, and so we can get some lateral or some see how those concentrations of ices change with distance. And that is slated for going to the lunar surface, I think, in 2023. So the next few years are really exciting for having different space agencies across the world go to the moon and collect more information about potential resources that are at the lunar South Pole, and also to just better understand what the character of that material is. And then finally, I wanted to end with Artemis. So Artemis is NASA's plan to go back to the lunar surface, to eventually create a base on the lunar surface. But in the intervening time, to use Viper to go back and characterize the lunar South Pole deposits, and then also send humans with Artemis 3 to go back and actually do a sample collection with humans from the moon. So you can see that artist that depicted in this artist illustration, where we actually have boots on the moon or humans on the moon again, collecting samples from the South Pole. And so I am running out of time, so I will stop there and take any questions that people might have.
Yeah, that's great. Okay, so we had a question that Dr. Smith helped answer in chat, but I'll verbalize it. But Joseph was wondering, how do you know that a meteorite came from the moon? And Dr. Smith was talking about how they compare the meteorite to Apollo samples, and also having a lot of data on the chemistry of the moon from the lunar orbiter helps identify that as well. Yeah. We also have the question, is there connection to similarities of moon and Earth rock to support moon formation from Earth impact?
Exactly, yes. So by being able to study moon rocks that we know definitively came from the moon, we've been there, we've collected them, bring them back to our terrestrial laboratories and analyzing them for their chemistry and their isotopic compositions. That's really been the key in allowing us to say, okay, the moon and Earth have this intimate history, and meaning that the proto-Earth was impacted by a very large impactor that was energetic enough to throw out Earth's mantle material, and then that material accreted in Earth orbit as the moon. But we only know that from, or it's been constrained by the chemistry of lunar samples and the similarities with Earth rocks, like this this person said. But also with modeling. So we've been able to tie the models, figure out how that actually happened. It's interesting that before the Apollo rocks were brought back, there were numerous hypotheses for how the moon could have formed. One was a giant impact, which is, variations of that are the model that's currently got the consensus of the community. But there were other models too, like maybe the moon was a captured asteroid that had made it into Earth's orbit and stayed there. That the moon had formed via a massive explosion, spontaneous explosion from the Earth, those kind of things. But the one that makes the most sense based on the observations, the physical parameters of the Earth and the moon, so how they are arranged in space, how they move, how they orbit each other and orbit the sun, And then their chemistry and their isotopic compositions are what really solidified that giant impact type model is the best explanation.
And Haley was wondering, does the moon have a global magnetic field?
So we think the moon had a global magnetic field in the past. I believe it's not present today, but we can actually see its past record in the rocks. So I don't know, I love explaining to people that rocks are great because not many people appreciate them. If you're out in the countryside or you're out exploring, you see a rock and you're like, oh, it's a rock. But actually rocks are the way we are kind of our roadmap to understanding the past. And so when we look at lunar meteorites and Apollo samples, we can see in some of them recorded paleo intensities or paleomagnetic field intensities that help us to understand that there was a magnetic field, 4 billion years ago on the moon, and it slowly waned over time. There are some variations in there, but we can actually read that rock record to understand how the magnetic field changed, which helps us to understand how the core and the moon's core was evolving over time, and also the moon itself from that point of view, which I think is fascinating. I always get so interested when people give talks on magnetic features of rocks. It's incredible to me.
Yeah, definitely. Very cool. Okay, Carol was wondering how different exactly are Earth rocks than moon rocks?
So there are a number of differences. So the general mineralogy, so generally the minerals are very similar, the compositions are very similar. But one of the big things that we notice between Earth and moon rocks is that moon rocks contain iron, nickel, metal. So on Earth, everyone's familiar with rust. And so rust is the effect of metals being oxidized, adding oxygen in and creating that rust. We don't see that in the lunar samples. We see iron present as its native form, not in an oxidized state. And so that's one of the big differences between Earth rocks and moon rocks, is that we can tell something about the oxidation state of the moon. We can say that there was less oxygen around. Other things, more kind of cryptic things that we see in the moon rocks is that they are really, we see differences in their isotopic compositions that we don't see represented on Earth. And also, as I mentioned right at the beginning, one of the big differences between Earth rocks and moon rocks is that the majority of moon rocks are ancient. So around 4 billion years old. And we just don't see those types of ages on Earth recorded in large amounts. And that comes back to the idea that, on the moon, we have this relic, basically, of the entire solar system's history since the moon was formed. But on Earth, we've had all of this erosion, we've had plate tectonics recycling material into the mantle of Earth. We've also had, human activity that to some degree has changed the shape of our planet as well. And so we just don't see these ancient materials. And so those are just a few of the ways that we can tell Earth rocks from moon rocks. Even though for some of their chemistry and isotope systems, they're very similar. So there are similarities, but there are also big differences as well.
Yes. Yeah, that makes sense. Okay, so we are running short on time, so I'm going to ask 2 more questions. One of them has to do with the picture that you are currently showing on screen. Okay. They're wondering if the astronauts are taking moon samples from the boulders and things like that, do they have to attach their tools to their suit some way so that it doesn't float away?
That is a good point. I imagine no, but I'm going to say I don't know.
Okay.
I think that maybe they're tethered somehow, but to, like you say, stop them floating away. It's not something I've thought about, so I don't know.
Yeah. Because there is some gravity on the moon. Yeah, but it's like how much would affect those tools since they're so small and things like that too. Yeah, great questions. We're not sure.
They're not sure.
Right.
Is that an illustration or that's a rendering? What is this image?
This is an illustration. So if you go to the NASA's Artemis pages, they've done an amazing job with creating these graphics of what we think exploration in the future is going to be like.
Mm-hmm.
They're really nice. I always like
Maybe they forgot the tethers. If they
Maybe. Yeah. Okay, and then my other question for you was, how did you end up studying moon samples? How did you get where you are today?
Oh, that's a really nice question. Actually, by coincidence. So I went to university to study geology. Actually, I went to study geography and volcanoes and switched to geology because I had decided I loved I loved rocks. And then I decided I wanted to take a path in research and do a PhD. But I wanted to study terrestrial systems. I was really interested in field work and getting out into the field and spending 6 months in the back end of nowhere, with my rock hammer and my magnifying glass and just looking at rocks and bringing them back to a laboratory to study.
Yeah.
But I wasn't fortunate enough to get a position doing that kind of PhD. And it so happened that at an interview for one of those positions that I didn't get, the advisor said, I have this other project looking at moon rocks. If you're interested, take a look at the job description and apply. And that's how I fell in love with planetary science. It wasn't on my radar. It just happened that someone opened the door and I walked through it.
That's wonderful. Yeah. So just the events lined up.
Exactly. Yeah.
That's great. Okay. All right. I'm going to share one final slide so that we can wrap up. Oh yeah, no worries. I can also. There we go. Okay, great. So I wanted to say thank you so much, Jess, for speaking with us today.
Thank you.
A ton of fun. And thank you all to everyone who tuned into this talk. Thank you to our North Carolina Space Grant and our members of the museum who help make events like Astronomy Days happen. And if you want to join our membership, the link is at the bottom of the slide here. You can just go to naturalsciences.org/membership and you can receive 10% off of the t-shirt and the hoodie that you see in the picture here. And you also get exclusive access to members only events and discounts as well. There are other great programs scheduled for these last 2 days of Astronomy Days, so we'll put the link in chat for how to register for those. And we'd like to hear your opinion of our programming this week. So we'll put our link to our survey in the chat as well. And if you registered for this program, we'll also email you that survey link too. And please let us know what you think so that we can improve our programming. And finally, since this program was recorded, it will be posted on our Astronomy Days program page. And so that'll be put up in the next few days. And so I just wanted to say thank you so much for attending. We hope you have a great rest of your day. Was there anything else that either of you needed to add? I'd like to add.
I just want to thank Jessica again for doing the talk, and I have to run to another talk, but thank you so much. That was really great to have you, Jessica. Thank you.
Thank you so much for having me. Thank you, everyone.
Great.
Thank you. Have a great day.
Bye.